Welcome to The Explainer. Today, we're going to do something pretty cool. We're going to build an atom from scratch, and in doing so, we're going to uncover the fundamental rules that literally dictate the structure of, well, everything.
All right, so let's start with a really big question. How does an atom even build itself? I mean, you have to realize atoms aren't just some random cloud of particles buzzing around. Nope. They are incredibly organized structures, kind of like tiny, perfect little buildings. So what are the blueprints for that? What are the architectural rules? And how on earth do electrons know exactly where they're supposed to go?
Okay, here's how we're going to tackle this. We're breaking it down into 4 key sections. First, we'll cover the ground rules, the absolute basics. Then we'll look at the 2 per room limit. What that means will become clear. After that, we'll get into the subshell seating chart, how electrons pick their seats. And finally, we'll put it all together to see the grand atomic blueprint.
All right, let's dive right in. Section 1, the ground rules. This is all about the most fundamental rule of all. Think about it. When a new electron joins an atom, where does it go first? There has to be a rule, right?
Well, it turns out it's all governed by something called the Aufbau principle. Now, Aufbau is a German word that literally means building up, and that's the perfect name for it. The principle basically says that electrons are, well, they're kind of lazy. They're always going to find the spot with the lowest possible energy available and fill that one up first, before even thinking about moving to a higher energy level.
Now, I know this diagram might look a little intimidating at first, but trust me, it's basically a treasure map for electrons. You just follow the diagonal arrows to see the exact order that the orbitals get filled. See? We start at the very top with 1s, then we follow the next arrow down, that takes us to 2s, the next arrow hits 2p, then continues on to 3s. But, okay, here's where it gets really interesting and a little weird. Look after 3p. The map shows that the next stop is actually the 4s orbital, before the 3d orbital. This is a super important point. The energy levels aren't always in a simple numerical order. The subshells from different main shells can actually overlap in energy.
So that's rule number 1. Let's move on to our next rule and keep building this atom. We now know the order the orbitals get filled in, right? But what about the capacity? I mean, how many electrons can you actually cram into one of these, let's call them orbital rooms?
The answer to that question comes from a brilliant physicist, Wolfgang Pauli, and his exclusion principle. It sounds complicated, but the core idea is this. No 2 electrons in the same atom can be in the exact same state. You can think of it like this. Every single electron has a unique ID, kind of like a social security number. This ID is made of 4 quantum numbers that describe its energy, its orbital shape, its orientation in space, and its spin. And Pauli's rule just says that no 2 electrons can have the exact same 4-part ID.
So what does that actually mean in simple terms? Well, it means this principle puts a very strict limit on how many electrons can live in a single orbital. And that limit, it's 2. That's it. Just 2 electrons per orbital, max.
But wait, there's a really important catch. To make sure their quantum IDs are different, if 2 electrons do share an orbital, they absolutely must have opposite spins. One is designated spin up, the other spin down. It's that final little difference that makes them unique and allows them to coexist.
And what's really cool is that this principle gives us a handy little formula to figure out the total number of electrons that can fit in an entire energy shell, that main level, represented by the letter n. The formula is simply 2n squared. So let's try it out. For the first shell, n equals 1. So that's 2 times 1 squared, which is just 2. Easy enough. For the second shell, n equals 2. So that's 2 times 2 squared. 2 times 4, which is 8 electrons. See? It's a really simple but powerful formula that comes straight out of these fundamental quantum rules.
Okay, so let's recap. We know the order they fill in, thanks to Aufbau, and we know only 2 can fit in each orbital, thanks to Pauli. But what happens when you have a bunch of orbitals that are all at the exact same energy level? How do electrons choose which one to go into first?
Before we answer that, we need a quick vocabulary word. Degenerate orbitals. Now, don't let the name fool you, it doesn't mean anything bad. It's just the official term for a group of orbitals that all have the exact same energy. The perfect example is the p subshell. It has 3 p orbitals, and they are all energetically identical. They're degenerate. This is where our third rule comes in, Hund's rule. And this one is my favorite, because you can think of it as the bus seat rule. Seriously, imagine you get on a mostly empty bus. You don't immediately sit right next to the one other person on board, right? Of course not. You find your own empty row. Well, believe it or not, electrons do the exact same thing.
And this illustrates it perfectly. Look at step 1. Let's say we have 3 electrons and 3 empty degenerate p orbitals to put them in. According to Hund's rule, you place one electron in each of those orbitals first. They all get their own seat. Then, as you can see in step 2, only when you add a fourth electron do you have no choice but to go back and start pairing them up. Electrons, it turns out, really value their personal space.
And there you have it. Those are the 3 key rules for building an atom. So let's take a step back and put it all together. Look at our complete atomic blueprint.
So here they are, the 3 rules of atomic architecture. Rule 1, the off-bow principle. Fill from the bottom up. Always start with the lowest energy level. Rule 2, the Pauli exclusion principle, the 2-per-room limit. No more than 2 electrons in any orbital, and they have to have opposite spins. And Rule 3, Hund's rule. Don't double up unless you have to. Spread out into empty orbitals first before pairing up.
So what's the big picture here? What's the key takeaway? It's that these 3 rules aren't just random. They all work together perfectly for one single purpose: to make sure the atom is as stable as it can possibly be. It's all about reaching that lowest energy configuration. And really, that's a deep truth about our universe. Everything in nature is constantly seeking stability.
And speaking of stability, our source material points out a really fascinating consequence of all this. It turns out that atoms get an extra little boost of stability when a subshell is either exactly half full or completely full. And why? It all comes down to symmetry. There's something inherently stable and balanced about those symmetrical arrangements of electrons.
Which brings us to a final, pretty deep thought. All these complex quantum rules, Aufbau, Pauli, Hund, they all seem to guide atoms toward this elegant, simple state of symmetry. And that symmetry, in turn, creates stability. So it makes you wonder, why is symmetry so fundamentally important to the stability of an atom, and maybe to the entire universe?